Operation of the internal combustion engine, or ICE. The internal combustion engine converts the combustion energy of the fuel inside the engine into mechanical energy. One type of internal combustion engine is the reciprocating piston engine. The vast majority of vehicles are powered by a 4-stroke reciprocating engine. In this video, we will go over the operation of such engines using the example of a 4-stroke piston engine powered by gasoline. We can now see the crank mechanism and the valve timing mechanism. The former is propelled by the energy released during fuel combustion and converts such energy into rotational, mechanical energy. The valve timing mechanism is needed to open the inlet and exhaust valves. It can be put in motion by gear, belt, or chain drive from the crankshaft. For the sake of simplicity, we will only review the operation of one cylinder. The engine's operation cycle consists of 4 strokes, or 2 crankshaft revolutions. The 4-stroke cycle is then repeated. Stroke 1 – intake. Stroke 2 – compression. Stroke 3 – power. Stroke 4 – exhaust. During a stroke, the piston travels between 2 extreme positions known as the top dead center and the bottom dead center. 2-stroke engines exist as well, but they are rarely found in cars. Stroke 1 – intake. The piston travels down from top dead center to bottom dead center. The cylinder volume expands, creating vacuum pressure. At the same time, the camshaft causes the inlet valves to open, allowing the fuel-air mixture to enter the cylinder. In modern-day vehicles, gasoline is supplied via an injector, whereas in the past, carburetors performed this function. The stroke is completed when the piston reaches bottom dead center and the inlet valves close. The second stroke is compression. This stroke starts at bottom dead center and ends at top dead center. All valves are closed. The cylinder volume is reduced, causing the fuel-air mixture to compress. The compression raises the cylinder's temperature and pressure. As the piston approaches top dead center, the spark at the spark plug ignites the fuel-air mixture. The stroke is finished when the piston reaches top dead center. The third stroke is the power stroke. This is the climax of combustion. The combustion process generates a large amount of heat, and the cylinder pressure can get up to 900 psi. The pressure of expanding gases causes the piston to move from top dead center to bottom dead center and turn the crankshaft via the connecting rod, thereby converting thermal energy into mechanical work. The stroke completes when the piston reaches bottom dead center. The fourth stroke starts at the bottom dead center and ends at top dead center. The camshaft opens the exhaust valves, and the piston expels the exhaust gases from the cylinder. When the piston approaches top dead center, the exhaust valves close, completing the last stroke, the exhaust, and the entire operation cycle. The operation cycle is then repeated. 3 subsystems feed the engine with fuel and air, and then expel exhaust gases. The intake system, the fuel supply system, the exhaust system. Furthermore, normal engine operation necessitates the use of the lubrication and cooling systems. The proper operation of these systems extends engine life. Please keep in mind that we are watching the engine in slow motion. In fact, the crankshaft turns an average of 700 revolutions per minute at idle speed. The upper limit on production cars reaches 8,000 revolutions per minute. Engine speeds in Formula One cars can get as high as 22,000 revolutions per minute. You can check the revolutions per minute value on an instrument called a tachometer on your car's dashboard. The operation of the engine begins with the car's starting system. The starter motor starts spinning, engaging the flywheel. The flywheel then stores the energy from the power stroke to use it until the next power stroke. The strokes alternate in different engine cylinders in a certain sequence. This is known as the engine firing order and is required for more stable engine operation. The firing order for this engine is 1, 3, 4, 2. It means that the power stroke occurs in the first cylinder, then the third, fourth, and finally the second cylinder. The sequence is then repeated. Please note that gasoline engines are spark ignition engines, since it is the ignition system, namely the spark plug, that ignites the fuel-air mixture. The primary goal of this system is to ignite the fuel-air mixture on time. Ignition timing is critical to the efficient operation of the engine. There is some time between the appearance of a spark and the complete ignition of the fuel-air mixture and the maximum gas pressure. The piston moves some distance during this time. For maximum engine efficiency, the piston must be within 10 to 12 degrees of top dead center at maximum gas pressure. It means that the ignition system must start in advance. The moment at which the spark plug fires is called the ignition advanced angle. The optimal ignition advanced angle is determined by crankshaft speed. The higher the crankshaft speed, the earlier the spark plug must fire. If the crankshaft speed is low, the ignition advance angle should be closer to top dead center. In modern engines, ignition timing, fuel injection, and many other tasks are controlled by an engine management system with the engine control unit at its heart, assisted by various sensors. The driver only needs to supply air, which is accomplished with the help of the accelerator pedal, also known as the gas pedal. Please keep in mind that in order to improve engine efficiency, the inlet and exhaust valves open and close prematurely and belatedly relative to the dead centers. The exact timing of the opening and closing of the valves is called valve timing. The optimal valve timing is set during camshaft design and does not change during engine operation. However, if the engine is equipped with a variable valve timing system, valve timing may vary during engine operation depending on the engine operating mode. Fuel-air mixture. The fuel-air mixture in gasoline engines is made up of air and gasoline. The mixture is prepared using a certain fuel-to-air ratio. Ideally, complete combustion of 1 kilogram of gasoline requires 14.7 kilograms of air. But in fact, the engine employs various mixture ratios. The ratio of 1 to 14.7 is the best in terms of power and economy. By reducing the amount of air, we get a more powerful engine but a poorer fuel economy. By increasing the amount of air, we get a more economical but less powerful engine. This range is suitable for normal engine operation. Further changes in the gasoline-to-air ratio will result in increased gasoline consumption and decreased power. Misfiring of the engine is also possible. This concludes our review. For more information on engine subsystems and other topics, watch our next videos. Bye guys!